Hi, my name is David Nolen. I'm a JavaScript developer at the New York Times. And in my free time, I like to contribute to various Clojure projects. One that I've been heavily involved in recently is ClojureScript. My talk is called ClojureScript, Better Semantics at Low, Low Prices. So I'm sure many people here at this conference are familiar with Clojure, which is a dynamic programming language that targets the JVM. It emphasizes functional programming as well as concurrency. Last year, Rich Hickey created a new implementation of Clojure that targets JavaScript. And at the time, he said something that I think is really important. While the JVM is great and offers amazing performance, it's really JavaScript that has the most reach, right? It's JavaScript that runs on your phone. JavaScript runs on browsers. So I think in order for Clojure to be more broadly adopted, this was a good decision. There's also something else to consider, which is that between three fairly large corporations, Google, Apple, and Mozilla, there's a strong interest in sort of having the best web experience. This means there's kind of an arms race going on between the various JavaScript engines. And as JavaScript developers and front-end developers, we're sort of benefiting from that. But I also think there's a growing benefit for people who might want to compile down to JavaScript, yet write in a different language. So, as this happens, people will probably, people say, why ClojureScript? Why not just program in JavaScript, right? Sort of adding something to your development workflow seems like a complication. I will say that this isn't a new idea, right? Google Web Toolkit's been out for years, and the idea there is that you have devs, they're extremely versatile, experienced with the existing Java tooling infrastructure, right? So something like Gwt, even as if I've been doing JavaScript for a long time, I don't care for Gwt, but based on your team, maybe that's the solution that you want to use. So this transpiles Java into JavaScript. There's projects like CoffeeScript, which is getting a lot of traction, and it's great because what's the idea here with CoffeeScript? It's let's take JavaScript, which is great. Let's sort of keep the things that we like, but let's sort of add improvements via sugar and a little extra bit of syntax. And this is really working out. People are happy to be able to target JavaScript with something like CoffeeScript. Then you have projects like Dart, which are very different, right? Dart is actually a new virtual machine for the web that's supposed to run in Google Chrome. And the idea here is that the problem that they're facing, right, is that no browser is going to adopt Dart, right, except for Chrome. Like Safari's not going to do it. Mozilla's not going to do it. You're not going to see Dart in Opera or anything else. So they also have to emit and generate good JavaScript. So I think in the next 4 or 5 years, it's not going to be that strange for developers to be able to pick whatever language they want, as long as that the language that they're using provides a compiler backend for JS. So that's just a brief introduction. I want to sort of frame this talk in terms of this famous Alan Perlis quote, Lisp programmers know the value of everything and the cost of nothing. And he's sort of making fun of the fact that Lisp programmers traditionally would write very expressive code that was horribly inefficient. So hopefully this talk will show that as Clojure and ClojureScript programmers, efficiency is actually really important. If we're going to adopt richer semantics in our language over the target language, JavaScript, we want to know that we're not paying too high of a cost, and there are various metrics that we're interested in there. So I want to start with the basics. The basics that any programming language is going to provide that's going to be useful for software development, is like arithmetic and operations on primitive collections. In this case, we'll look at JavaScript arrays. So here is a simple JavaScript expression. I'm sure many of you are familiar with JavaScript. If you're not, it's not too hard to see how this is similar to something you might write in a language with Java or C-like syntax. So here we define a variable called x. We add two numbers together, and we put it into x, right? Simple stuff. In ClojureScript, it's going to look a bit like this. It's not going to be dramatically different. But the thing that should jump out at you is, it has this sort of S-oriented S-expression syntax. The other thing to know is that in JavaScript, the plus is an operator, right? So JavaScript sort of has this rap for being a sort of very dynamic language. But because of the sort of adoption of the Java syntax, lots of things are static that in Lisp are dynamic, right? So this is plus, but it's a function. In Clojure, that's a proper function, right? To show, like, this is not valid JavaScript, right? Functions are values, right? You can pass them around. But in JavaScript, plus is not a value, right? You can't do this. This is perfectly valid in Clojure, right? You're totally allowed to call apply, and the argument is a collection, because functions are values in Clojure. Another case where JavaScript is very sort of static, right? Array access, right? When you're accessing properties and objects or arrays. Again, this is something that's not a first-class operation in JavaScript, the language. And that's not the case in ClojureScript. And really, I'm going to use Clojure and ClojureScript interchangeably in this talk. So this totally works. But this also works, right? I can construct a Clojure vector, which is like a JavaScript array, and I can drop plus and aget in there. If you're familiar with functional programming, this is not a new idea. Functions are values. JavaScript sort of waves its hands here around operations and various primitive operations. So we actually get around this in ClojureScript, because the sort of warning signal that should go off is that if those things are not like primitive operations, how is this efficient? Are array accesses slower in ClojureScript? Is addition slower? Fortunately, that's not the case. We have a series of solutions that we come upon in getting ClojureScript to produce good JavaScript. We have compiler macros. And there's other reasons for compiler macros, but one thing that they're really awesome for is that we can optimize non-higher order usage of functions. If you're not using functions as values, we can use them to inline the primitive JS operation. So this is great. We get performance and we get generality, right? We get the exact same semantics. As long as you're not doing higher order stuff, we're going to produce highly optimal JavaScript code. So the next thing I want to talk about is control flow. When you write a language, it's very common to write if something, some test, and else something, what have you. If you're going to do that, right, you're concerned about what constitutes a truthy or falsy value in your language. So you'll write this in JavaScript, but of course this is problematic if you've done enough JavaScript. 0 is falsy, and this will cause the false branch to execute. Same thing for the empty string. If you've encountered this and had a bug from this, you're going to feel a bit like this, right? So those are JavaScript statements. This is a Clojure expression. Clojure is expression-oriented. I don't know if you caught Jeremy's excellent talk on CoffeeScript, and I think a couple other languages were this way, but ClojureScript is expression-oriented. Expressions always return values, and JavaScript is kind of this weird mix of statements and expressions. So ClojureScript is definitely expression-oriented. So here's the if expression in Clojure, and we're saying if x, true, false. If x is 0, right, that's not a falsy value. The same for the empty string. The only things that are falsy in Clojure are nil and false. There are no other falsy values. But this means that when we emit the code, we have to emit a check. Any place that a conditional occurs in ClojureScript, and when we compile it down to JS, we have to have this check, this extra function call where we guarantee that the value of x wasn't 0 or the empty string, right? From a performance perspective, I mean, this really makes you feel a bit like this. It's not nice, right? It's very slow. So again, a lot of the things I'm talking about are going to be a little bit in the realm of implementation details. These strategies might change over time, but perhaps you'll see that we solve some of these problems, and it'll also give people ideas how to solve these problems themselves. So how we got around this is we actually have type hinting. So Clojure on the JVM actually uses type hinting to avoid reflection during interop. In this case, we decided to add a Boolean type hint on all the core predicates. Now this is a dynamically typed programming language, and so we don't really want to go around littering our code with type hints. So we're taking a page out of Robin Milner's book. Robin Milner designed this beautiful language called ML, which became standard ML. Currently people use OCaml, and Haskell also derives from this lineage. And his idea was that if we're going to use types, we really don't want to have to annotate our code. If we are, we might as well be programming in Java, right? We should let the compiler do the work for us. So ClojureScript has a very limited set of type inference around some key stuff. We actually do inference on let and if. Fortunately, Clojure's a Lisp. We always build everything off of primitives. And the two sort of common Boolean operations and or are actually written in terms of let and if. So this largely eliminates all calls to our truth test. And this is critical in places where literally the only thing is happening are array operations and bit operations, which are critical in the design of fast, persistent data structures, which we'll see in a little bit. So now if we write this code, instead of emitting this, right, this is what we would have emitted had we not done these previous optimizations I just talked about. We would have called a function called less than, and we would have had to have checked that the return value was actually Clojure's notion of truth. This is what the ClojureScript compiler emits, because we both inline the comparison operator and we use type inference to remove the check. So that's nice. But the real building blocks in Clojure, and this actually holds true for JavaScript as well, are functions. Where it gets interesting is that Clojure is a little bit different from JavaScript, and then in JavaScript, functions are a primitive construct. And actually, it's true for Scheme and Common Lisp as well. Clojure actually takes a page out of the book of this programming language called T, which was a sort of dialect of Scheme in the 80s. So T, at the bottom of T were objects. Even functions were constructed in terms of objects. So this is legitimate. This is a legitimate type of thing to do in Clojure. I can construct a type that can act like a function. Right? This is actually used quite a bit in the standard library. Collections are often provide an interface such that you can use them as functions. So on this bottom line, I'm able to construct an instance of that type, and I can invoke it just like a function. Again, if you're a JavaScript developer or know anything about JavaScript, this should give you pause, because how is that going to work? You can't call objects as if they were functions. We were lucky in this case that there's a different calling convention that's thoroughly supported in JavaScript, where you can take the function, you can say .call, you can pass a context followed by the arguments. And this is how we get around this, right? We always emit invocation as a .call. So this way, we can call functions and objects in exactly the same way. Once again, if you have an eye for performance and you've seen the cost of this in the JavaScript engine, you feel a bit like this, right? It's like you're taking a hit for doing things this way. So again, fortunately, there's an aspect to ClojureScript development that lets us surmount this problem as well. And that's Google Clojure. When Rich Hickey designed ClojureScript, he realized this is a Lisp. We're going to be writing macros. We're going to be generating tons of code. And he saw that Clojure really has a good strategy for controlling the amount of code that gets generated. So Google Clojure is very aggressive about dead code elimination, constant folding, function inlining, everything. But what that means, the important thing about that is that we can optimize invocation specifically because ClojureScript users already engage in whole program optimization, right? So this optimization that I'm about to show you can't normally do in an interactive setting, but because everybody's using whole program optimization, it's OK. We propagate function information the same way we propagate Boolean type-in information, like whether the function returns Boolean. Because we know things like how many arguments does the function take? Does the function have rest arguments? This is all information that we propagate. And again, we only do this during when a developer is basically producing the production build of their application. Because again, we would otherwise impede interactive development because we're actually putting statically determined things if we optimize during interactive development. We don't want to do that. So this pattern is extremely common inside the ClojureScript code base. If you look at the internal functions, there's a lot of this going on, right? We actually take advantage of the fact that we have language level support for dispatching on arity. You often see this pattern occur in JavaScript, but it's not very nice, right? So if you say arguments, the list of arguments will get reified inside of your function, and then you can sort of access them as if it was an array-like thing, but of course, it's not really an array-like thing. And JavaScript programmers do this, but there's a performance hit. Any place where you do this, the function calls will be twice as slow. So what we do in the ClojureScript compiler, it's what we do is, if you're not doing whole program optimization, we just use the slow calling convention. In a multi-arity function, what we actually do is we create we produce all the arities inside of a closure, and we return a function which actually dispatches on the number of arguments we've received to an internal to each case. But what we do that's a bit clever is that we actually export each one of those arities as properties on the function that we return. And this is because JavaScript programmers are crazy, right? They're adding properties to functions. They're adding functions to functions and expecting that code to be fast, right? It's the habits that JavaScript developers have that we've been able to leverage in this case. So by exporting them this way, and when we go through whole program optimization, this is extremely fast. The bottom code is what we generate, and there's zero overhead doing it this way. So that's a lot of stuff. We've talked about basic operations. We've talked about how we handle Booleans. And we've talked about how we optimize function invocation. So I want to put a bit of these puzzle pieces together. And I can do this with a meaningless benchmark, where we're going to compare how fast the JVM is to JavaScript to the JS that's generated by the Dart2JS compiler and the JavaScript that's generated by ClojureScript. Just real quick, I want to show some source code. I'm not going to show the Java, because the Java doesn't even fit on one slide. This is the code for spectral norm off Alioth, the benchmark site. So this is the JavaScript. It's actually quite nice. It's pretty terse, pretty concise. Here's the code for ClojureScript. And if you notice, it looks pretty much the same. We have a lot of arithmetic. We have a lot of primitive JS operations where we're mutating JS arrays. And here's the Dart. The Dart is also pretty concise. So let's see these guys running. Call time and pass in. OK. So let's see. Java's pretty quick at this. This is single-threaded. This is not multi-threaded. If it was multi-threaded, Java would win. But we're going to do a fair comparison. So 9 seconds. Let's see how fast the JS is. Oops. I don't know if you've been following JavaScript development, but JavaScript is really fast. Not quite as fast as Java, but I think it's going to be much faster than you think if you haven't been following along very closely. 12 seconds, 13 seconds. That's pretty good. That's within shooting distance of the JVM. So here is the Dart-generated JavaScript. So Dart got a lot of flack in the beginning because it produced pretty crazy JavaScript and it wasn't that efficient. They've made huge strides. That's pretty good, 13.8 seconds. So there's some things that they do which are not totally optimized yet, but that's also not bad. So here is the ClojureScript generated JS. So again, all the optimizations that I've shown you are required to see the running time that I'm showing you here. Right? 13 seconds. It's basically neck and neck with the handwritten JavaScript. So all the optimizations that I've shown are in play here to make this work. All right. So performance is great, but it's only interesting if we're doing something with that performance, if we're really leveraging that performance. If our compiler is doing those optimizations, what are we doing with it? And this really turns out to be great in how we implemented persistent data structures. So ClojureScript has the full suite of Clojure collections, persistent lists, persistent vectors, persistent hash maps. And these are real hash maps. In JavaScript, you often objects sort of double as hash maps. Here, we can actually have arbitrary keys. We have proper sets. And these collections are quite a bit cooler than just implementing some mutable version of these things in JS yourself. These are based off of Okazaki literature as well as Phil Bagwell. And really the power behind persistent data structures, once you sort of get used to them, you kind of get annoyed when you don't have them, especially good ones like the ones that Clojure has. So when we go back to this first line of code, and what's nice about this line of code, part of it, is that we say 1 + 1, and we don't think twice about it. The value of 1 is not going to change underneath us, right? We're sort of thinking about values, and we know that's simple to think about. But that flies out the window as soon as you have mutable collections like JavaScript arrays. So here I have an X, and I assign it to an array. I add something to it, and I assign it to Y. Well, now X and Y point to the same aliased thing. That's mutable. Who's going to change that? This is actually a real problem. Even in a language that's single-threaded like JavaScript, you see MVC frameworks do a lot of cloning, right? Like you have a collection, and some client wants to use that model to do something, and you have to defensively clone that because you don't want that person to destroy your data. Again, this is something that is not a problem in Clojure at all, right? Here we have a let expression where we bind X to a persistent vector. We add something to it, and we bind that to a local Y, and we've changed nothing. There's no aliasing going on here. We have the same clarity that we have in expressions where we write code about numbers, right? Collections have that same kind of clarity. So Clojure's persistent data structures are very clever, very well designed. They're based on this 32-way branching. The thing that's been really shocking about persistent data structures is how good V8 is. I mean, when ClojureScript first came out, it was all copy on write, right? They were just trying to get ClojureScript out the door. It was all copy on write data structures. Those were quite slow. People were very skeptical that these could be ported successfully. And it's turned out that not only have they been all ported and we use them, the way that the engines are going, it's pretty incredible. So here's some, whoops. Here's a benchmark off JS_perf, right? So the thing that I want to point out is, it's very hard to tell with benchmarks like this who's cheating. But Chrome tends to be fairly, I think, good about the numbers that we see. So what this benchmark is doing, we're comparing how fast we can add 1 million items into an array, right? Just numbers. We're just pushing them onto an array, a mutable array. Then we're testing the same operation on persistent vectors. And then we're testing that operation on a really clever local mutation of persistent vectors called transients, which are really nice. So in Chrome, the shocking thing should be persistent vectors are almost within 3x of arrays, right? That's pretty nuts. When you're adding the millionth item to the persistent vector, right? There's no copying. You don't have to do that copy on write. It's quite good. On V8, it's even more amazing that transients actually outperform arrays. And who knows why, but that might be because with persistent data structures, we know the size of the arrays that we're going to use, and the behavior is very consistent in our code. So this is, building collections, sure. What about doing more interesting operations like reduce? So the numbers start getting really close here, right? So we actually call the internal reduce that's provided by arrays, right, in all the browsers, and we're comparing that to our own handwritten reduce in the JS that we create. In Chrome, this is not even, maybe this is 1.5x. In Firefox nightly build, where it's even. And Opera and Safari are not so bad. Safari, it's like, OK, maybe we're 8x slower. But to put this in perspective, let's look at some other numbers, right? So you often hear JavaScript people talk about performance, and it's usually sort of grating because they're talking about performance but not really thinking about what their applications do. So here I'm building an array, right, with 1,000 elements. Then I'm measuring how fast I can write to local storage. Then I'm testing how fast it takes to do a ID selection with jQuery. It's 164 times slower than building an array. So there's this thing, right? We've got persistent data structures. The cost is so low that it's not going to be the bottleneck in your application. And just to show you that I'm not pulling your leg, let's take jQuery out of the equation, right? Even though everybody's using it. Let's just call document get element by ID. And you can still see that transients beat that out. We can build transients faster. And the performance of persistent vector is really not that bad. So, OK, persistent data structures, that's cool. They're only as cool as the interface that's provided by the language. And this is actually where I think Clojure really shines. It's built on a very solid set of abstractions. For example, I can call first on a persistent list. I get 1. First on a persistent vector. I get 1. I can call first on a persistent hash map. And of course, hash maps aren't ordered, so I'm going to get some key value pair. Same thing with sets. I'm not sure what I'm going to get, but I'm going to get something. But I can also call first on things which are not Clojure at all. JavaScript strings, right? So I can call first on a string and get the first character. And we'll talk about why that's interesting in a second. So clearly, first is polymorphic, right? We have all these collections, and we have a polymorphic function which can uniformly treat those data structures. So in JavaScript, the only analog is this, right? People create a type called foo, and it implements bar. People implement a type called baz, and implements bar. And then somebody writes a function, was. It takes an x, and we just call bar on that x. This is duck typing, right? That's all that it is. And the problem with this, and you see this in JS libraries, is that all the APIs for doing basically the same things. They're all different. So Clojure wisely has a core set of protocols that expects all developers to implement. You're not going to make up your own. Yeah, you can make your own sequence type. That's fine. But it better satisfy this interface because we want that code to work everywhere. So when you define a protocol, it generates polymorphic functions that different types can then implement. The other thing that protocols do, they actually do a little bit more than that, and they solve the expression problem, right? So something that was popular in the early days that's really powerful, but nobody does it anymore, is that you can modify prototypes, prototypes of natives, like built-ins. Like you can add functions, methods to array, string, date, regexp, whatever you want. And this is really powerful, and people did this. But now that we have a lot of JavaScript code, it's just roundly looked down upon, right? It's just the interop story is not good. You're going to run into clashes. But the thing to note here is that people want that not because it's actually a bad thing to do, right? The reason you don't do it is because JavaScript has no support, right? As programmers, we do want to locally modify types that we don't control and add functionality to them, but JavaScript doesn't give you any way to do that. But this is totally fine. Actually, in Clojure, we can safely extend types we don't control, and it's totally legit. The modifications are local. Other people won't get screwed over by your cool idea. And the other thing that's nice about protocols is protocols also do this really nice thing where they support providing a default case. So you can actually add functionality to all types in the system. And this sounds, you can actually do delegation with this. And it sounds a bit esoteric, but we actually use this internally because we have a protocol called iHash, because we want all objects to be legitimate keys inside of a hash map, right? We want that to work. So we add hashing to all objects. And again, safely, without modifying the prototype. So I just want to show the BrowserRepo. So what this is about is that, if you're going to work in a compiled language, you want the story to be good about the interactive development. Like when you have this other language and it's not JavaScript, well, suddenly you lose the ability to open up a console, type in the language that you want, and interact with the language that you want, right? That's a huge cost, right? Why would you do that? Actually give up all that great tooling. And ClojureScript can't answer all those problems, but we can at least answer the interactive development part. So there's no Emacs in sight. So this is a browser-connected REPL. So when I'm typing code over here, right, that's actually getting compiled and sent to the browser over a Google Clojure cross-page channel, and that JS is getting evaluated, and the browser's returning the value back to my REPL in my source code editor, right? So I can do stuff like, I want to get this box, right? And you see over here that prints out, which is pretty cool. The other thing to note is that, which I don't have time to talk about too much, but in ClojureScript, everything's namespaced. So that's going to get evaluated as cljs-stl.browser.demo.box. That horrible thing that JavaScript devs never want to do, which is properly namespace their code. So this is all stuff that the ClojureScript compiler magically does for you. I can just type box, but when it gets compiled, it's properly namespaced. So if I want to make this blue, I can make it taller. Maybe I want it to be short. Make it spin around. That's pretty nice. And note that I'm actually working in my source file. This is something you can't do in JavaScript, right? In JavaScript, you're sort of copying and pasting and like doing this wacky stuff. Here, I never have to leave my source code file. All right. So this is the last section of my talk. I want to talk a bit about macros. So this is the sort of like, you know, the golden pot in the sky that's cool about Lisp. So I want to talk about this thing. Those of you that were lucky enough to see Dan Friedman's and Will Bird's talk will know about what I'm going to show you. And this is the zebra puzzle. And this is actually what got me excited about, actually really got me excited about macros and Lisp and logic programming in general. So in December 17th, 1962, in Time magazine, there was a really fun puzzle that was published, and it's called Who Owns the Zebra? And the puzzle basically is about 5 houses, and each house has 5 properties. What's the nationality of the person that lives there? What do they like to drink? What cigarette do they smoke? What color is their house? And what pet do they have? And so the puzzle goes, you know, there are 5 houses. The Englishman lives in the red house. The Spaniard owns the dog. Coffee is drunk in the greenhouse, and so on. And it ends with the question, after you have all these conditions, who drinks water and who owns the zebra? In his amazing book, The Paradigms of Artificial Intelligence Programming by Peter Norvig, he actually shows how to build Prolog inside of Common Lisp twice. The first one is a very slow interpreted one, and then he shows again how to do the sort of efficient compiled one, and he actually shows how beautiful it is to solve this problem once you can embed Prolog in your language. He also points out that it's pretty challenging. It's a pretty challenging constraint satisfaction problem, right? There are 24 billion candidate solutions. So after Peter Norvig finished his optimized Prolog compiler for Common Lisp, he was able to solve it in 1993 in about 17 seconds, which was at the time probably extremely impressive. So Dan Friedman, William Bird, and Oleg Kiselyov, who are all here at Strange Loop. Hopefully you saw Dan and Will's talk, and Oleg's talking tomorrow, I think. But they came out with this book in 2005, and they showed a different approach to embedding a Prolog-like system into Scheme. And it's an amazing book. It's very short, 180 pages, and I highly recommend it. But I got fascinated with it, and I ended up implementing it in Clojure. And then I got invited to JSConf, and I was like, hey, I'm going to JSConf. I'm going to port core logic to ClojureScript from Clojure. And ClojureScript is just Clojure, so it took me like 2 days, right? It wasn't hard to do. And what's beautiful about the mini camera system is you really can define your constraints exactly as the problem description is sort of written. So here at the top line, we see milk, right? So we're saying there are 5 houses, and the person in the middle house drinks milk. And then we say the Norwegian is in the first house. The Norwegian lives next to the blue house. To the right of the ivory house is the green house. And literally, we can sort of encode those sentences basically verbatim. And so then the question is, you know, OK, that's really cool. We got this. This is going to run in JavaScript. And the question is, how fast is it? I'm going to run this, the compiled JS for this program against V8. Right? 16 milliseconds, right? That's pretty insane. 1,000 times slower than what Peter Norvig was doing on a very beefy workstation in 1993. I can do this in my browser, right? And the correct answer is at the bottom. We see that the Norwegian drinks water, and the Japanese man owns the zebra, because those are the 2 blanks. So now, this doesn't quite explain why macros are great. I mean, and so I'm going to show a bit of a comparison here. So this is the whole source. This is exactly what I compiled down to JavaScript. It's tiny, right? So Mihai Bazan, who is very cool, he works on ES CodeGen, and very clever. He did this thing called amb.js. This is what the JavaScript looks like for solving this, right? So the benefit here with macros is that, say you have this idea, I want to do logic programming in my language, right? All you're going to be doing is fighting the syntax. Whatever syntax was decided, I guarantee you, in a C-based syntax, they weren't thinking that you might want to do this, right? And the contortions are pretty insane in this code, and again, he did as best as he could with what JavaScript lets you do. I want to have time to take questions, and there's just too much things to talk about. So if you want to see more examples of you know, what does ClojureScript offer over JavaScript, you can go to this URL, and there's some good examples there. I want to end the talk with saying that there are costs involved, right? It's not like ClojureScript is totally awesome. I think ClojureScript is really great, but with adoption of any technology, people need to be more realistic about what it is that you're offering, right? There are real costs associated with adopting something like ClojureScript. A big one, if you care about this kind of thing, is that we, for performance reasons, we just adopt JS numerics as broken as it is wholesale, right? We don't want to have our own number system because we want the persistent data structures to be fast. This is a challenging problem to overcome, and we'll see if we solve it. The other thing is that, let's be honest, yes, interactive development's cool, but debugging is a problem, right? We sort of assume that the ClojureScript developer knows something about JavaScript, right? Because we're going to generate JS, and in ClojureScript, unlike something like CoffeeScript, where CoffeeScript truly tries to produce readable syntax, ClojureScript, all we try to do is produce high-performance code that allows us to match the semantics of Clojure. We're not trying to produce the most readable JavaScript. Again, we hope to address that in the future with source mapping. It's also not bootstrapped. Honestly, it's not something we care that much about, but people they always ask us, is it bootstrapped? Is it bootstrapped? And it's not bootstrapped. You have to use Clojure to leverage ClojureScript. You can't just use JavaScript. There's also the thing, this may or may not be a plus or minus, depending on your perspective, right? We're going to hear a bit about Dart, I think, later today. And there is a lot of benefit in the amount of engineering resources you can pull together with a corporate language project. ClojureScript is completely volunteer. And then there's the thing where it's like ClojureScript is a year old, but it's still pretty alpha, again, volunteer-oriented development. And a lot of these performance enhancements are not evenly distributed. If you're familiar with Clojure, it's a bigger deal than if you're not. If you're just coming to ClojureScript, you're like, this is cool, and you like it. But if you're a Clojure programmer, there are many things that are strangely slow that shouldn't be. There's also the fact that, like, again, Dart in the beginning got a lot of flack for producing crazy amounts of code for Hello World, which was, I think, kind of not much of a valid criticism, but it's true. It does seem strange that you have to generate so much code. The same problem actually applies to ClojureScript. If you write Hello World and you generate a file, it's not going to be small. The flip side of that is that we have heard stories. People now have ClojureScript programs that are 5,000 lines long, and that ends up being pretty nuts, right? We end up generating like 1.8 megabytes of JavaScript. But the thing is, we have advanced compilation on our side. So when those apps actually get compiled down by that, you're down to 40K gzipped. Just to put that in perspective, jQuery is 32K gzip. So the advanced compilation is actually extremely good on real applications. And then, of course, Alpha Project. There are lots of small details in ClojureScript which are just not done. And these things that are present in Clojure, missing in ClojureScript, and these things add up. So last thing I want to say is my involvement in ClojureScript has been kind of fun because I don't actually contribute that much to the JVM Clojure project, but I've been having a lot of fun contributing to the Clojure project, ClojureScript project, and sort of getting familiar with the internal details. And the shocking thing is that the compiler is ridiculously small, 4,000 lines of code, right? The actual true compiler is less than 1,000, I think. Same for the analyzer. So that's 2,000 lines of code that don't have to do with loading up Google Clojure and running advanced compilation, all that stuff. Clojure is truly a simple language, right? A lot of the complexity in the compiler is avoided, again, because of macros. The macro file, I think, is actually bigger than the compiler, right? So hopefully this is interesting, and people are excited about trying it out, perhaps contributing to it. Thank you for listening, and if there's time, I'll take some questions. So the question was, a lot of the concurrency constructs are missing from ClojureScript. That's sort of because JavaScript is single-threaded. Web workers are cool, but they're not a good fit yet because web workers involve a lot of copying overhead, right? If you pass a value to a worker, it's going to try to walk the whole graph and copy the whole thing. It's extremely slow for the kinds of workloads we want to do, for example, reducers. Reducers are a pretty cool new feature in Clojure which allow you to do parallel operations over the standard collections. There's going to be a talk on River Trail, I think, at Strangeloop. It's worth seeing if it hasn't already happened. If it has already happened, go check it out. We would love to see the browser vendors be more serious about some form of parallelism that JS can take advantage of. That's more useful to us than workers. Is there a way to export the persistent data structures to non-ClojureScript clients? Yes, it is possible. I do have a little project that does that. Part of the problem is that when you export them, it is still a lot of code. You might just want a persistent vector or just a persistent hash map, not the whole thing. I haven't quite figured out how that's going to work. But yes, that's, I think, going to be kind of nice that if you want to just pull out persistent vector and use that in JavaScript, you'll be able to. So how easy is it to create a JavaScript library, an interface such that a JavaScript library can call into your ClojureScript code? It's quite easy because this is a problem that Google Clojure has to solve, right? It has an export functionality. You can say, Google Clojure, don't munge all my symbols. These symbols need to stay unchanged because some outside consumer needs to access that functionality. So no, we're not. We don't cache. We just use the garbage collector. We don't cache previous versions. But it does mean that you'll see worse performance on browsers that don't have good GCs. And it is the case that I'm sure if somebody did some memory benchmarking, that is a cost, right? We do generate more garbage than if you're writing it all mutable in JS. We can't fix. We can't fix that. Though I will say that it's nearly impossible since everything's obfuscated for you to know, and each build those obfuscations will be different. So there's no way for an external JS library to know what your fields are going to be called, right? There's no consistent naming, and that's because of Google Clojure. So IE, I think their new engine's called Chakra, and it's supposed to be really good. I should have tried to run that benchmark, but I didn't. But from what I've heard, it's extremely good. I'd expect it to at least be in Safari territory, perhaps not V8 territory. Yeah, so Swing.js is pretty cool. It's one of these things where you have to sort of like be an Emacs user. You have to like be sold on that. That's why I try to demo outside of Emacs, even though I personally am an Emacs user. There's a version of so the question was how many things, like there's lots of libraries that people like in Clojure. How many of those have been ported to ClojureScript? There are a lot, and every day there's more. There's a port of Hiccup to ClojureScript. Yeah. So the question was what's needed to port Clojure to ClojureScript? There are significant differences. Some of these we hope to mitigate in the future through perhaps a language feature. But for example, a big one is that we don't have runtime macros, right? Clojure has runtime macros. So any code that relies heavily on macros existing at runtime, you need to move those to another file, and you need to make sure that your logic doesn't depend on the fact they're available at runtime. So the question is, what are the roadblocks to having the ClojureScript being bootstrapped? There are actually a couple things that are big for us that maybe other people don't care about. One is we really need to decide on the AST. So we don't even want to go there until we know what a good Clojure AST looks like. But that aside, it's really, we need to have the full reader, right? The full reader needs to be there. We actually need to have some solution for the runtime macro problem, probably. We have to make decisions. Again, there's some tension here as to whether we'll really do that. If we'll do it, maybe somebody else will do it. I'm not sure if we'll do it. But there's also issues around the fact that namespaces in ClojureScript are just objects, right? It's just object properties. Whereas in Clojure, their namespaces are like a reified entity. And that's also true for vars. And that's not the case in ClojureScript. Perhaps those things are surmountable. I haven't thought about it too much. No, there's no ClojureScript at the New York Times, sadly. It's like I tried to say that in the beginning, right? You pick the tool for the team. I have a lot of fun doing ClojureScript. It's been exciting to see people build products on ClojureScript. One of the most exciting is Lighttable, and he's going to talk about that. I'm sure he has 6 or 7 or 8,000 lines of ClojureScript now. So I don't get to use it, but it's great to see other people using it. So I started working on source maps. It's getting there. It's probably maybe a couple hundred more lines of code. I've just been busy, so it's not done yet. So the question is, can you eval? Sorry if I haven't been repeating the question. Can you eval ClojureScript in the browser? No. The browser doesn't know anything about ClojureScript. So there's a really nice hacker. His name's Evan Mazeski, but he built a tool built on Leiningen, which is the Clojure build tool. And it's pretty awesome. So you can watch files, and it'll auto-compile them. It also, like when I was showing you the ClojureScript interaction inside of Sublime, I'm using line CLJS build to do that. So it has lots of useful features. So that's it. Thanks.